Hello again, AP Calculus students. Mr. Record here from Avon High School. We are going to take a look at our third example in the shell method, also known as the method of cylindrical shells. I call this topic 8.12 Part B from the College Board course and exam description, although there is no such thing as a Part B. It's because the shell method is, once again, not part of the BC curriculum, would not be tested on the AP exam, but you could use the shell method if it did make the setting up of the volume that you were trying to find a little easier. And of course, for students that are taking Calculus 2 at the college level, you'll definitely see the shell method in your course. So we're going to take a look at our third example, which says the shell method is preferable. So let's see what that kind of pans out here to say in a second. So it says find the volume of the solid formed by revolving the region bounded by the graphs of y equal x squared plus 1, y equals 0, x equals 0, and x equal 1 about the y-axis. As always, I'd like my students to sketch the graph and draw representative rectangles when needed. So this is a problem where I would say the student might be responsible for generating this plane region because the graphs, the equations, the functions are more accessible in this case, as opposed to a couple of my earlier examples, 1 and 2, where that may not have been the case. So we're going to go ahead and use a blue pen to sketch our y equal x squared plus 1. Notice that we do have a scale adjustment here. Each block is a half of a unit. So by the time we graph the point or plot the point 0, 1 and 1, 2, and we understand that this is going to be a parabola parent graph y equal x squared just shifted up 1 unit, I believe that that's as much of this as I would have to sketch. Yes, there are other portions of this graph that do exist out in the world, but we're not going to need them because when we graph y equals 0, also known as the x-axis, and then in, say, green, I'll graph x equals 0, also known as the y-axis, and then let's say purple, x equals 0. That's this vertical line, or x equal 1, sorry. That's this vertical line here. It's probably easy to see that I don't need those extraneous parts of that parabola because I have a shaded region. So let's color this region in yellow here. Oh, so nice and satisfying, right? It's like ASMR. Calculus ASMR. All right, so we got our shaded region. Now, this is where I really want students to develop an appreciation for the method of cylindrical shells. Because if we were going to rely on our disc and or washer method, I want you to think about this. We're going to revolve around the y-axis. So obviously that's a very important part of the problem. So there's our axis of revolution. There's our little revolution action right there. And if we were going to use the disc or washer method, think about it for a second. Which of the two would we have to use? And if your answer was yes, you are correct. You have to use both of them, don't you? Up here, we're going to have a washer method because we have the two representative rectangles indicated like that, right? But down here, we only need one representative rectangle because there is going to be no hole. Right about here is where the rule would change, right? So if we wanted to set this up with the disc and washer, we'd have to use two integrals. Furthermore, the thickness of each of these rectangles is a change in y, right? Change in y, change in y, which means we have to write our functions in terms of y, which means we'd have to get an x by itself, and that's even more laborious work, right? So let's abandon all that idea and focus on this cool method called the shell method. And for the shell method, all we have to think about is the word that rhymes with shell. You guys know that word, right? I've talked about it before. Parallel. So draw the single representative rectangle so that it's parallel to the axis of rotation. Obviously, the change in the distance or width is a change in x, so that means you can set this up with respect to x. So our blue equation is all good to go. And then you just simply need to recall what the actual setup for the shell method is. And remember, it has a 2 pi in it. You would integrate from some boundary A to some boundary B, and then you have this thing called the radius, P of x, times the height of your representative rectangle, which we call h of x. And so if we just bring each part down, I'll worry about the limits of integration last. I tend to have my students focus on the h of x first. Leave a little space for that p of x. You won't need much space. And the h of x is just simply how long that rectangle is. And we can figure that out by just taking the equation of the top minus the equation of the bottom. Well, the equation of the bottom is just 0. So really, it's just the x squared plus 1 that's going to account for the actual height h of x. Now, the part that some students make harder than they need to is the length of the p of x. And p of x is just simply this horizontal distance that exists between the axis of rotation and, say, the middle of our rectangle. And sometimes kids will say, oh, that's a half. Well, that's because I put the rectangle halfway in the middle. But what if I put the rectangle, let's say, oops, you move back there, line. I don't want you to move, but let's move the rectangle here. Now what's the distance? Or here, what's the distance? Or here even? Well, it turns out it's just a distance of x, right? Every single time that you have a y-axis serving as the axis of rotation, the p of x will be x 100% of the time. And so all we have to do is plop an x in there. Right? Be nice if we put the dx here because it does have meaning. It's not like it's going to have a big role, but it should be there. And then the boundaries or the limits of integration have to be x values. So reluctantly, do not say 0 to 2, right? Because those are y coordinates, y values. 0 to 1 are the x values that truly exist between the places where you could put this vertically drawn rectangle, okay? And so that's going to finish out our problem. Now, a lot of times with my students, I'm tempted to just stop right here because the integration is fairly trivial at this point. But if we wanted to get the exact answer here, we could go ahead and most likely distribute the x. And then you see that we were just taking the antiderivative of a polynomial. So I'm going to do this because it's just fairly quick. So there's our integration of x to the third, our antiderivative. X squared over 2 is the next one. We're going to evaluate that from 1 to 0, which you have to be honest, those are probably the 2 easiest boundaries of integration that you can work with. And so now we're going to plug in a 1. 1 squared and 1 to the 4th is still 1. And then if we plug in a 0, that's just going to wipe everything out. And so if we get a common denominator of 4, 1/4 plus 1/2 is 3/4. If you want to keep working on this, you could reduce the 2 and the 4, and you would get a final answer of 3 pi over 2. And that's what this area, volume would be of this shape that would probably look, I don't know, it's kind of something like this, I suppose, once all is said and done, but it's kind of difficult to draw this in a three-dimensional fashion. But that's nonetheless the volume, and much, much easier if we're doing the shell method. We got one more example of the shell method in a future video if you want to check it out. But I think after you do these 3 examples that I've already shown at this point, you ought to be getting pretty darn comfortable with it. Hopefully that's the case. Anyhow, we'll see you next time.